Okay, so this is the second part of the video where I'm going to help you walk through the worksheet here. I didn't mention in the first part, but if you wanted to do this at home and you're watching the video, you can certainly, just choose two varieties of something, right? So in the past, we used to use like goldfish crackers that were goldfish flavored or pretzel flavored, or you could use real licorice, or you could use like Skittles and, different like two varieties, one that's your favorite and one that's not your favorite. And you can certainly, go ahead and collect that at home. You don't have to just passively do whatever that I got. You can certainly, find something at your house like Cheerios versus mini wheat, something like that. Anyway, so let's go ahead and take a look at this equation and try to decipher what's going on here. So again, we have these genotypes, right? We have the black variety is either capital B or capital B lowercase b, and then the red variety is lowercase b. Those are the three possible genotypes. And so when we're looking at this first equation is looking at genotypes, okay? And it's derived really, I think this is important to see, it's derived from a Punnett square cross, right? Where you take like the P and Q, which really P represents the, in this case, the capital B. And Q represents, I'll use the red, it represents the lowercase b, okay? So when you do this Punnett square cross, I'll use black there. So this one is that. And isn't that, basically the same thing as saying P squared, right? P times P. And so P squared represents, here it is on here, P squared represents this homozygous dominant genotype. And then, if you're going to fill out a Punnett square, wouldn't this one be Q and Q? Right, so that would be Q squared, right? Because bring the Q's over and across. And so Q squared, wouldn't that be the same as saying little b, right? And then this intermediate here, 2PQ, would basically be, this hybrid offspring where it's PQ. Or another way to say that would be big B, little b, where you're getting that, that hybrid offspring. So 2PQ is saying that there's two of those Punnett square boxes that are big B, little b. And so that'd be the genotype there. Of course, those would phenotypically, both of these would phenotypically be the black variety of licorice, because the black is dominant. And so the heterozygous genotype would still produce the dominant phenotype. Okay, so that top equation, again, is just showing, this one right here is showing phenotypes. I'm sorry, it's showing genotypes. So this would be the dominant homozygous genotype, recessive homozygous genotype, and this would be the hybrid genotype, okay? And this lower equation here, right, this lower one is really showing just the alleles separately, okay? So P would be the dominant allele, and Q would be the recessive allele, okay? So each equation just kind of shows genotypes, and where's the one come from? That one, it just means that, one is representing a percent in decimal form. So like if you add up all of the dominant and recessive alleles in a population, you're gonna have 100% of the alleles, right? Because there isn't an additional, there's just two here. And so like, for instance, if this was like 70% and this was 30%, 0.3 and 0.7 is 1 or 100%, you know what I'm saying? So that's where that one comes from. It comes from the fact that if you add them all up, it's going to be 100%. Okay, so let's see what we've got in our table and see if we can use these equations to our benefit and try to walk through solutions to filling out this data table. This data table was set up a certain way to make it easier for you to do these calculations. We're gonna walk through these columns from left to right here. Okay, and so we'll start with Q squared. Okay, what is Q squared? Well, again, Q squared is the recessive genotype. That's all that it's saying. It's the recessive genotype. So if Q squared, if we had 5 of our licorice varieties, 5 of 10, right? Because there were 10 total. 5 and 5 is 10. There was 10 total. So 5 out of 10 were red. And then what is that in decimal form? That's 0.5. So Q squared is basically taking your percentage of, and I'll write it up here, it's your percentage of the recessive genotype in decimal form. So, you know, like the next one, what is 3/10, right? 0.3. So I'm just going to do, by the way, I'm going to do the first 2 rows because I think, you know, you can do the rest of them if I show you how to do the first 2. So then how do we go from Q squared to doing the next column? How do we go from Q squared to Q? Well, if something squared is 0.5, wouldn't you just, you know, unsquare it? Yes, and so how do you unsquare Q squared? Well, if you take the square root of that number, you're going to get this number. So what we're going to do is we're going to take the square root of 0.5. Let me grab my calculator. Sorry about the pause there. Here it is. So on my calculator, I have to use the second function for this one, but square root 0.5 is 0.7071 and so on. I'm just going to round to the nearest hundredths place. So the square root of 0.5 is 0.71. Square root of a decimal seems weird. If you're not sure, go ahead and take 0.71 times 0.71. You're going to go back to 0.5. But anyway, that's the right number. Square root of 0.3 is 0.5477 and so on. So I'm going to round that to 0.55. Okay, moving on. And I'm just going to show you what we've done is we've started with this, right? And why do we start with that? We started with that because we know that. If we know how many of a population are the recessive phenotype, we know that that is the recessive genotype, and so we can start with Q squared, and then we unsquare it, or take the square root of it, to get that value. So we're going to work this basically from one equation to the next, working in a counterclockwise fashion. I don't know if that's a trick that helps you to understand how to do these or not. So next we're going to actually go and figure out P, because if we know P plus Q equals 1, and if we know Q, for instance, in the first row is 0.71, if we know this is 0.71, well, what plus 0.71 equals 1? Well, just take 1 minus 0.71. That's pretty straightforward. You could probably do that in your head. So 0.29 must be P. 0.29 plus 0.71 equals 1. That's a true statement. So P is 0.29. And again, just what does P represent again? It represents the dominant allele. And what does Q represent again? It represents the recessive allele. And again, I just want to illustrate that these two together, added up, remember, equal 1. So I can just double check, does that equal 1? Yes. Okay, let's do the next one, 0.55. That would be 0.45. Again, 0.55 and 0.45 equal 1. And again, I'm using this equation here, P plus Q equals 1. So now I have determined this. Then in order to figure out what P squared is, well, that's easy. I just square it on my calculator. That shouldn't be too difficult. So then we're going to be here next. So to fill out the next column, what's P squared? Well, what's 0.29 times 0.29? .0841, so I'm just going to round to the hundredths, 0.08. And what's 0.45 squared? Oops, did it wrong. 0.45 times 0.2025, so 0.20. Almost done. We know every value now so far except for what 2PQ is. Now, again, 2PQ just means what is the heterozygous genotype frequency. Remember, because that's from the Punnett square, that's why there's a 2 there. We're not going to multiply anything by 2, we're just going to fill in what that value is. So if we know, for instance, P squared is 0.08, 0.08. If we know Q squared is 0.5 for that first row, 0.5. Well, finish this statement. So 0.8 plus something plus 0.5 equals 1. Well, okay, 0.5 plus 0.08 is 0.58. So what plus 0.58 equals 1? Well, just take 1 minus 0.58, and you're going to get 0.42. So again, much like these numbers added up right here, equal 1, that's that same idea that these numbers right here equal 1. If you see that or not. And then let's do the next row. 0.3 and 0.20 is 0.50, so this must also be 0.50. So again, this Q squared plus P squared plus 2PQ equals 1. So that's, that's what you're doing as you're filling out this column here. Hopefully the chart helps you. But again, if you're not looking at the chart, you're just looking at these equations and saying, well, in a problem that I'm going to do, I'm going to pretty much be given the recessive genotype, or have to find the recessive genotype. What's that as a decimal percent, basically, as a frequency? I take the square root of it to get Q. I do the difference of 1 to get P. I square that to get P squared. And I take the difference of this plus this of 1, and I get PQ. So that's how you walk through these. Here's the class data that you can use to fill out for your worksheet. So go ahead and use these. This was from my first hour. I'll do the first row here for you. So 43 divided by 43 plus 37 is 80. So the total would be 80. 43 divided by 80 would be Q squared as a frequency. 43 divided by 80, 0.54. Take the square root of that for Q. .74. The difference, Q and P equal 1, so 0.74, or 1 minus 0.74 is 0.26. Square that, 0.26 times 0.26, 0.07. Again, I'm rounding to nearest hundredths. And then this plus this plus something, plus 2PQ equals 1, so 0.54 plus 0.07, 0.54 plus 0.07 equals 0.61, so this must be 0.39. So those three numbers, 0.54 plus 0.07 plus 0.39 equal 1. So there you go, I've filled that one out. So again, remember that these values together equal 1, and these values together equal 1. Okay, so hopefully this goes all right for you. Fill out this class data, and then you're going to make a graph of that. So don't forget our acronym dry mix, right? So if we're going to plot the Q and P values, all right, you might want to use a key where Q is a red dot, and because it's representing to the lowercase red licorice allele, and P is a black dot or something like that because it's representing the black licorice, uppercase B allele. So plot both the Q and P values. Those are the dependent or responding variables. So Q and P frequency must go on the y-axis, and the frequency values are going to go between 0 and the highest frequency you'll get is be like 1. So this probably be like 0.1, 0.2, 0.3, 0.4, and so on. 0.5, 0.6, 0.7, 0.8. And then this right here would be generation. And you know, like generation 1, 2, 3, 4, and 5 or something like that. The title of this would probably be like allele frequency in a licorice population over 5 generations, or allele frequency in a red and black licorice population over 5 generations, something like that. Let's go ahead and plot the data. I would imagine that you're going to get one of the lines increasing and one decreasing because red licorice appeared to be consumed the most, and so black licorice as a population was almost a favored phenotype, you'd say, because even though it wasn't favored by the predator, it was favored by the population, and it was the phenotype that ended up being increasing in frequency. So this is an example of, you know, microevolution of a population changing over time in terms of the allele frequencies in a population changing over time. So good luck with this worksheet. Definitely use the Principles of Life textbook, page 298 to 299 to finish up, and take a look at the Hardy-Weinberg conditions for that, and you can use that for a few of these other questions as well if you need to. All right.